Find the volume of the solid obtained by rotating the region bounded by y equals xe to the negative x for x is greater than or equal to 0. And this region is going to be rotated about the y-axis. So the graph is provided for you. That's the function xe to the negative x. It's going to be rotated about the y-axis. So washer or disk don't make sense because of the fact that you'd be using a rectangle that would be perpendicular to your axis, but then this function here, xe to the negative x, would be both the right endpoint and the left endpoint of that. So it wouldn't allow you to do disk or washer. So we draw a rectangle that's parallel to the axis so that we can do shell. It's going to be an x. This rectangle is upright, and it gets moved from left to right. So we'll be in x. And we have the formula for the volume using shell. Well, necessary in this is for us to be able to figure out the radius and the height. And so the way you get the radius is by attaching the axis to that typical rectangle. That distance there is the radius. It happens to also be, in this particular problem, the distance off the y-axis. And so we know that's x. And so therefore the radius is x. The height's a little easier to get. It's how tall the rectangle is, and it goes up to the function. So the function is xe to the negative x. That's how tall the rectangle is going to be. As it moves from some starting point to some ending point, the starting point will be x equals 0, but it's going to go on forever, off to infinity for the ending point. All right, great. So we have the setup, and now it's just our job to multiply the x's together, and we have x squared e to the negative x, and we're integrating from 0 to infinity. It's improper, definitely, because this upper limit is infinite. And so now it's our job to basically address that by coming up with a variable and letting that variable approach infinity. Let's go with t. So the volume will be 2 pi times the limit as t goes to infinity, the integral from 0 to t of x squared e to the negative x dx. The major two parts that are left is our job to integrate, which will be somewhat trouble, and it's our job to evaluate the limit. Let's integrate first. Well, how are you going to integrate x squared e to the negative x? Well, the way you do that is by recognizing that you need integration by parts. And so what's nice, though, is that you can use the shortcut to integration by parts. Whenever you have a polynomial term times an exponential term, you can use this shortcut where you differentiate the polynomial down to 0, x squared. One time would be 2x, the derivative. The derivative of 2x is 2, the derivative of 2 is 0. And then the other part, the exponential part, gets integrated the same amount of times. So the antiderivative of e to the negative x is negative e to the negative x. The antiderivative of that would be positive e to the negative x. And then one more time you get a negative e to the negative x. And then what you do is you multiply along diagonals that are going down and to the right and apply alternating signs, and it does all the integration by parts for you. It actually performs integration by parts twice in this example. We get uv minus the integral v du, and then that in turn we would need another integration by parts, but here it's all together. We get it as multiplying along these diagonals and applying the alternating signs. We know exactly what the antiderivative is quite quickly. It's a shortcut. We have negative x squared e to the negative x, negative 2x e to the negative x, and a negative 2 e to the negative x. Okay, great. So that's our antiderivative. We've integrated. Let's plug in the limits. We put a t in to replace all the x's, and then we put a 0 in to replace all the x's. It'll help us, though, if we simplify beforehand. Factor out what they have in common. They all have an e to the negative x, and represented as a fraction will be helpful as well. So we'll put the e to the x in the denominator, and we'll have this negative x squared, the negative 2x, and the negative 2 in the numerator. Okay, great. Now let's plug in the t, and let's plug in the 0. And let's deal with the 0 part while we can before we go fill out the limit, figure out what the limit is. Plugging in 0 gives you 0 and another 0 and then a negative 2, and then the denominator is e to the 0, so that's negative 2 over 1. But then it's upper limit evaluation minus lower limit evaluation from the fundamental theorem of calculus part 2. And so that's just going to be a minus of negative 2 or a plus 2. Okay, and on the next slide, we'll attack the problem of trying to figure out what the limit is. But we've integrated. Now we need to find the limit. So what is this limit as t gets big? Well, the numerator is going to be negative infinity, I'm sorry, because we take a large number and square it, but then we multiply it by negative 1. We take a large number and double it, but then we multiply that by negative 1. And then the negative 2 really doesn't affect it. But basically, the numerator is going off to negative infinity while the denominator is getting very large. E to a large number is very large. And so we have this indeterminate form. It's negative infinity over infinity. Write quotations around it. It's not an actual number. It's just a symbol that stands for some number that we don't quite know what it is. We have to actually perform L'Hopital's rule to figure out what it is. There's no algebra that we need ahead of time. We can just go ahead and do our first iteration of L'Hopital's rule, which requires you to take the derivative of the numerator and divide that by the derivative of the denominator. So numerator's derivative is negative 2t minus 2. Denominator's derivative is just e to the t. And now we check this limit instead. L'Hopital's rule says that they are the same. Thinking about a large number here and doubling it, it's large, but then times negative 1. So basically, we have another version of negative infinity over infinity. But there's nothing to stop you from using L'Hopital's rule again. And notice that each time in the numerator, the power on t is getting smaller. The next time through, we'll just have a negative 2 as our numerator. And then this we actually get a number for, not another form of negative infinity over infinity. The numerator staying constant at negative 2. It's the denominator that's getting very large. If you have a constant over a denominator that's growing, then what happens is it's going to go to 0. Okay, great. So the limit is 0. Well, then we have the 2. Don't forget about the 2 pi from the formula for shell, and then basically the 2 from the evaluation of the integral at the lower limit, and so then our final answer is just 4 pi.